Okay, let's dive right into this explainer and tackle a massive, honestly frustrating challenge that literally every single Cambridge computer science student faces. Whether you're building your foundation in the IGCSE syllabuses like 0417, 0478, 0983, 0984, or 2210, or you're stepping up to the big leagues with the AS and A-Level 9618 syllabus, this is for you. Today, we are mastering IDE features. Specifically, we're looking at initial error detection and dynamic syntax checks. Now, you might be sitting there thinking, yeah, I know what an integrated development environment is, but listen to me. Knowing the textbook definition and knowing how to extract maximum marks from a Cambridge examiner are two completely different things. It's like a totally different game. We are going to analyze exactly why students, like our hypothetical candidate, let's call him Alex, completely overload their answers with raw facts, write a whole essay, but score terribly. And on the flip side, we'll look at students like Sam, who rush through the paper, panic, and entirely miss the critical command words. The goal today is to break down the actual psychology of the exam. We are getting right inside the examiner's head, so you never lose these silly marks again.
Now, what's really interesting about this question on the screen is that these concepts, evaluating exactly how efficient an algorithm is and explaining how IDE syntax checks function, they appear in literally every single examination series. Seriously, go look at the past papers. You will see these questions time and time again. They are predictable. Yet, despite being so predictable, students consistently lose crucial points on them year after year. Why does that happen? Well, it's because they lack structured reasoning. When the pressure is on, students tend to treat computer science as a test of memorization, just a brain dump of facts, rather than a test of logical step-by-step problem solving. Examiners are practically begging you to show your working and your analytical depth, but most candidates just throw definitions at the page, cross their fingers, and hope something sticks. We are going to completely fix that approach today.
To secure those maximum marks, here is our roadmap for today's explainer. We'll start with getting inside the examiner's mind, move on to mastering cognitive domains, break down the method mark strategy, look at the top 3 examiner warnings, and finish up with your ultimate exam blueprint. Let's kick things off with Section 1, Inside the Examiner's Mind, and demystifying IDE error detection. Before we can even talk about your overarching exam strategy, we absolutely must define the core principles we're dealing with here. Initial error detection and dynamic syntax checks are the specific features within an IDE that automatically parse your code in real time. Think of it like a highly technical spell checker. They're actively working in the background as you type, identifying and flagging syntax errors before you even attempt to run or compile the program. But here's the catch. We aren't just memorizing these definitions to parrot them back. The examiner requires you to prove mastery of how they function in a real-time scenario. When they ask you about this, they want to know that you understand the background processes. They want you to explain how the IDE is continuously comparing your specific keystrokes against the programming language's strictly defined syntax rules. It's about demonstrating that dynamic relationship, not just reciting a dictionary definition. Moving right along to Section 2, Mastering Cognitive Exam Domains. This is all about proving concept mastery. This table on the screen brilliantly illustrates the academic benchmarks you are up against. You really need to internalize this. Knowledge and understanding is just your baseline. That's your mastery of fundamental principles, like simply knowing what an IDE stands for. But look at application. This is where things get real. The examiner requires connected, conceptual understanding transferred to completely unfamiliar contexts. They're going to give you a scenario you have never, ever seen before in your textbook. Finally, analysis requires logical, structured reasoning. Top-performing students don't just state facts in a wide, shallow pool. They demonstrate deep analytical depth over superficial breadth. They prioritize explaining the why and the how, digging deep into the mechanics of the code rather than just listing out what things are. That depth is what separates the top grades from the rest. So you're probably wondering, how do we systematically hit those higher-level cognitive domains every single time? Well, we use the PEAL framework: point, evidence, explanation, and a link. Every single analytical paragraph you write must contain these 4 elements. You make your point, you back it up with evidence pulled directly from the prompt, you provide the explanation of the computer science theory, and crucially, you link it back to the specific scenario. This framework is literally your armor against losing marks. Now, before we continue, subscribe to our YouTube channel, AC Exams, at @ACEXams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's jump into Section 3, the method mark strategy. This is how we process for points. In Cambridge Computer Science, marks are heavily awarded for the process of clear working, not just arriving at the correct final answer.
If we look at these flawed responses side by side on our imaginary exam paper, we see exactly why our two hypothetical students, Alex and Sam, lose out on top grades. Let's look at Alex first. Alex is the classic over-explainer. He spots the word IDE and proceeds to write a massive paragraph, completely overloading the page with raw computer science facts about compilers, interpreters, and debuggers. But there is absolutely zero analytical depth regarding the specific question asked. Alex gets maybe 1 mark for knowledge if he's lucky. Then we have Sam. Sam is constantly watching the clock. He rushes the response and completely misses the specific command word requirements. The prompt explicitly asked to evaluate, but Sam merely described. Both of these students fail to deconstruct the question and extract the relevant data properly. If you imagine red pen marks all over their papers, it's not because they don't know computer science. It's because they simply don't know how to take a computer science exam. To actually secure those method marks and magically turn those red pen marks into green check marks, your data interpretation must explicitly show these 3 steps on the page using correct terminology. Whether you are dealing with IDE syntax checks or evaluating complex algorithm efficiency, you have to extract the correct data first, sometimes pulling it straight from confusing binary representations. Then you must perform your calculations or logical steps with perfectly clear notation. Do not skip steps in your head. Finally, you draw evidence-based conclusions. If you systematically write these steps out one by one, the examiner can award you method marks for your transparent process, even if a simple, silly arithmetic error messes up your final conclusion. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's move into Section 4, the top 3 examiner warnings and how to avoid the principal pitfalls. Listen up, because these are the exact traps waiting for you on exam day, pulled straight from the examiner reports. Number 1. Examiners constantly report that students confuse cause and effect regarding IDE error detection. A student will write that the syntax checker actually caused the program to fail, rather than correctly explaining that the syntax checker detected a pre-existing violation of the language rules, which would prevent compilation. See the difference? Number 2. Forgetting to check boundary conditions and edge cases. When evaluating an algorithm, students always test the normal data, but totally forget to mention the extreme, weird data inputs. And number 3, the biggest trap of all, providing generic answers that are not specific to the context given in the question. I'm telling you, this last one is the absolute biggest killer of grades across the entire syllabus. Okay, let's play a little game here. Take the next 60 seconds to scan this comparison on the screen and really absorb the difference. The generic flaw on the left reads, "Dynamic syntax checks find errors in the code quickly." Sure, it's a true statement, but it scores absolutely 0 points for application because it's too vague. Now look at the context-specific fix on the right. That dynamic syntax check highlights the missing semicolon and the specific while loop provided in the scenario. Do you see the difference? Notice how the context-specific answer explicitly links the theoretical IDE feature directly to the exact scenario, the exact loop type, and the exact syntax error provided in the prompt. That precision, that linkage, is the literal difference between a C grade and an A star. Let's see how this builds into algorithm evaluation. When the examiner asks you to evaluate algorithm quality, which is notoriously one of the most difficult question types, you cannot just write down "it runs fast" or "it takes up less memory." You must execute a structured speed write of your Peel paragraph to address these 4 specific higher-order elements. You need to talk about time complexity, how the execution time scales with the data. You need to discuss space complexity, how memory usage scales. You must address those edge cases we talked about, and finally, evaluate the overall effect on system performance. If you systematically address these 4 bullet points, you are absolutely guaranteeing that you hit those higher-order assessment objectives that demand you to evaluate alternatives and justify your recommendations.
And now we arrive at Section 5, the ultimate exam blueprint. This is your procedural framework for success. This 5-step systematic processing sequence right here is your cheat sheet. It is your ultimate guarantee to hitting every single assessment objective the Cambridge examiners throw at you. Step 1, deconstruct the question and identify the key elements and command words. Step 2, apply the relevant theoretical principles, like defining dynamic syntax checks, accurately. Step 3, execute your analysis with crystal clear working. This is exactly where you earned those sweet method marks we discussed. Step 4, Verify your results against the specific scenario provided to ensure they actually make logical sense. And step 5, present your final answer using correct, precise computer science terminology in the appropriate format requested. If you follow this standardized sequence, your answers literally become bulletproof.
Following that sequence effectively relies heavily on 3 golden rules that practically guarantee top marks across your entire 9618 paper or whichever syllabus code you're sitting. Rule number 1, command word decoding. You must know the exact difference between state, describe, explain, and evaluate. They require completely different depths of response. Rule number 2, strict Peel framework application. I cannot stress this enough. Never, ever make a point without linking it back to the scenario. And rule number 3, a strict time management matrix. Do not spend 15 minutes perfectly crafting an intricate answer for a 2-mark question like our friend Sam might try to do in a panic after realizing he rushed the first half of the paper.
Now, if that command word demands critical or comparative analysis, you must execute these 4 specific rules. You cannot just list the features of 2 different IDEs in separate paragraphs and call it a day. You must actively identify the similarities and the differences. You have to force yourself to use explicit comparative connectives, words like whereas, conversely, or in contrast. You must support every single comparison with hard evidence from the given data, and finally, draw concrete conclusions about their relative importance to the specific scenario. This structured comparative process is exactly what the examiners are desperately searching for when they are grading those massive, high-value 6 or 8 mark questions. Give them what they want. And this slide brilliantly illustrates the ultimate takeaway, coming straight from the Cambridge examiners themselves. Look closely at this quote pulled directly from a principal examiner report. The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. I'll say it again. Context is king. You can have the most beautiful encyclopedic knowledge of IDE features, initial error detection, dynamic syntax trees, and algorithm efficiencies. But if you do not directly link that knowledge to the messy, specific problem the examiner has placed in front of you, you will simply not access the top marking bands. Always, always link it back. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.